Let's move on to layer normalization. We saw layer normalization when we were doing transformer architectures. And at some point, we were actually seeing them when we were doing LSTMs and recurrent neural networks. This is an assignment for you to watch that video, so I'm not going to spend too much time on this slide. I'm going to go really fast through it, and then you can ask questions. So the question that we want to answer is, or the observation that we're going to start with, is that when it comes to recurrent neural networks, or in general, when it comes to data that are sequential, like sentences or a speech, you're going to have different length for your input sequence. Some sequences are going to be shorter, some sequences are going to be longer. And in those cases, which are unlike images, there is this observation that batch normalization doesn't perform quite as good when it comes to helping the model converge. And there is actually a mathematical reason for it when it comes to sequences, especially when it comes to recurrent neural networks processing your sequences. Your architecture is going to end up being as deep as the number of elements in the sequence. So it's going to be as deep as the sequence length. Now imagine you have a recurrent neural network, which is going from bottom to top. And then in the first few layers, for most of your data, there is going to be layers. There is going to be some mean and some standard deviation of that layer, and they make sense. And you're computing them based on the size of your mini batch, and maybe your mini batch is 32 or even bigger. And these mean and variances are actually good estimates of your mean and variance. But as you go deeper in your neural network, some of your sequences are shorter. It means that your recurrent neural network for them is going to be shorter. And some of them are going to be longer. It means that some of your data in the mini batches are going to survive when you go deep into your layers. It means that if you look at a particular layer now, there is going to be less observations to compute the mean and standard deviation upon. And this is going to lead to fluctuations in the gradients that you're going to compute later on. And in some cases, you're computing your statistics perhaps based on only one observation. And this is a problem, and it is especially problematic when it comes to recurrent neural networks. Even for transformers, if you think about it, if you have a short sentence, you're going to pad it. And then that attention mechanism, and then the layers that are going to come on top of it, you're going to have difficulty computing these statistics. So some of these for longer sentences are going to exist. For some of them, for shorter sentences, it's just zeros. And then you're computing your mean based on a lot of zeros. That's why when it comes to recurrent neural networks, when it comes to LSTMs, when it comes to GRUs, when it comes to transformers, we usually use layer normalization. And each one of them, if you want to compare them, there is batch normalization, weight normalization, layer normalization. Each one have their own pros and cons. They all have some good invariances, which are going to be different. And it's the idea of there is no free lunch. Any questions about layer norm? Up until recently, people were thinking that layer norm doesn't work for images that well, but there are actually some papers recently in 2022 that show that layer norm also works for convolutional neural networks and images, and that depends on the architecture that you work with. So you need to make some minor modifications to your convolutional neural networks, and the most important one is that inverted bottleneck type of layers that you have in language. You're going to borrow them and take them to images and CNNs. And then layer norm is going to also work for images. Okay? Was everything clear? Okay, perfect. So there is a question in the chat about, is that the same bottleneck in UNet or similar? And no, it's different. And in UNet, you have shortcut connections. So those are not bottleneck. The bottleneck layer, think of the fully connected portion of a transformer block. On top of the attention, you're going to put a fully connected layer. And that fully connected layer is going to take you from low dimension to 4 times bigger of a dimension in terms of your channels, and then it's going to project back into low dimension. So you go from D model being your dimension to 4D model being your intermediate dimension, and then you go back to D model. And that's why it is called inverted bottleneck, because usually our bottlenecks take us from high dimension to low dimension and then high dimension because you want to save parameters. This one is inverted. You go from low dimension to high dimension, then to low dimension. Does that answer your question?
Yeah, thanks.
Okay, perfect.
Hey, Professor. So yeah, I've been reading contrastive based methods recently, and yeah, the thing you said about convolution. So recently, what author like the people who are working in contrastive methods for like unsupervised image representation learning, they are saying is that they've been replacing all the batch normalization methods with actually layer normalization methods because they hypothesize that using batch normalization kind of makes their tasks and like the learning sort of trivial because large model starts to learn the batch statistics or the relationship between images in the batch, which shouldn't be there. So yeah, I mean, right now, yeah, convolutions in image and video like space or like the vision space. More and more models, more and more people are using layer normalization.
Yeah, so you're correct. And actually, in part 1 of the course, we go over all of these.
Oh, that's good. Yeah.
Yeah. When it comes to convolutions, we study a large class of them, and even the modern ones. So yes, you're right. And there are also some delicacies when it comes to batch normalization. That one we cover in part 1 of the course, so I don't want to spend too much time on it. But when it comes to batch normalization, and when you want to scale to multiple GPUs, you have to be very careful. Are you going to compute the statistics of these layers or these hidden units per each GPU? And each GPU is, let's say, consuming 32 images? Or are you going to compute your statistics based on the entire population that you're spreading among your GPUs? And usually the way that things work is, and the correct way of doing it, not only for computational reasons, but also, and for efficiency, but also for mathematical reasons, for you to be optimizing the same thing in your loss function, you have to do it per GPU. So let's say you are doing data parallelism. You have 8 GPUs in front of you. Each one is consuming 32 images or 32 data points. Then you need to compute your statistics based on 32 per each GPU, rather than based on 32 times 8 is going to be 256, I guess, rather than doing it based on 256.
I see. So the way I've seen some of the codes which implement like like over parallel over multiple GPUs is that they sort of accumulate gradients from the different GPUs, combine them, and then they do like the back propagation stuff.
Yes.
But yeah, it's kind of tricky. Yeah.
But you have to be careful with the batch normalization.
Yeah, that's true. Yeah, otherwise, yeah, it'll learn the dependency between the training cases or it. Yeah, that's true. Yeah, yeah.
Yeah. Okay, perfect. Any other questions about layer norm? And there are also some other issues when it comes to batch normalization. When you have data in the form of images, text, or speech, you're fine. You can have good or large enough mini batch sizes. But when it comes to video or 3D point cloud or other types of data, then you're going to run into trouble. You cannot fit enough data and process them on a GPU to give you accurate estimates for your mean and standard deviation. Because simply a video, when you push it through a deep neural network, is just not going to fit. You're going to run into memory issues. And this is one of the reasons people are going away from batch normalization or are looking for alternatives. But at some point in time, it was actually influential. Without batch normalization, your neural networks wouldn't converge and you wouldn't see any results. Okay, perfect.